In this lesson, let's look at how to solve exponential equations that have different bases. Here's our strategy. To solve exponential equations that have different bases, we're going to first take the natural log of both sides, and that seems completely off the wall, but it works because as long as we do it to both sides, we can do whatever we want, and our logarithm rules are going to help us out. You'll see how in a few minutes. Remember that natural log is just log base e, so there's nothing fancy about it, but the reason we like log base e is because our calculator has a natural log button. You could actually use any base log. You could do the log base 5 of both sides or the log base 2 of both sides if you had a calculator with a log base 5 or a log base 2 button. But we don't. We do, however, have log base 10 on our calculators, so these could just as easily be done with log base 10 if you really wanted to, but I think it's more standard to do it with natural log, and our textbook requires us to give the answer in terms of natural log, so we'll do that. It's just as easy as anything else. Okay, after you do the natural log of both sides, you're going to use the power rule to move the variable out of the exponent. This is why taking the natural log of both sides was such a genius move, because if you have logarithms you can use the log rules, and that lets us take the exponent and put it down where the coefficient belongs, which makes it easier to deal with. And after that, all you have to do is solve the little linear equation that you get. Okay, here we go. First example, 3 to the x equals 20. Now notice that I can't write 20 as a power of 3. So instead, to get around that, we will do the natural log of both sides. You just simply write ln in front of each side. Now our next step is to take this exponent and slide it down into the coefficient position. Okay, now we have just a plain old equation. It doesn't look very plain to you probably because we have these logarithm expressions, but it's true that ln3 is just a number. It's not a whole number, but it is just a number. So if you divide both sides by ln3, you'll get this, ln20 over ln3. And you need to, now, if you want to get a decimal approximation, get your calculator and punch in ln20 divided by ln3. Make sure that if you do, after you do ln20, that you close the parentheses before you hit the divide key. So ln20 divided by ln3 is 2.73. Make sure and try this out on your own calculator so you can make sure that you know how to get that answer. Here's another example with base e. So we're now going to take the natural log of both sides. Okay, and then our power rule helps us out. We can take that exponent and put it down in the coefficient position. And all we have to do now is divide both sides by ln e. But I don't know if you're already thinking this, but you may be thinking, well, how do I get ln e on the calculator? Well, really, you don't even have to worry about it, because remember, we talked about when we evaluated logs, as long as we're in log base e, we can say, what is the exponent of e that gives us e to the first power? Well, the exponent ought to be 1, right? So ln e is just simply 1. So I replace that ln e with a 1, and then the equation is solved. X equals the natural log of 2.1, and that's all we have to do. We might use the calculator, to get a decimal approximation. But notice this too. This is the same answer we could have gotten if we would have switched from exponent form into log form. See, e to the x equals 2.1. If we switch it into log form using what we learned in a previous lesson, then we would say log base e of 2.1 equals x, but we wouldn't write log base e, we would write natural log of 2.1 equals x. And then you can use the calculator to get your decimal approximation. Okay, here's another example. In this case, I have a coefficient on my 7. And I need to get rid of that coefficient before I start trying to do the natural log of both sides. So here I have isolated our e to the x, and e to the x equals 15 over 7. And you're going to now do the natural log of both sides of that. Take your exponent and slide it to the front. Okay, now remember that ln e is simply 1. And there you have it. X equals natural log of 15 over 7. Now, if you actually want to use the calculator to get a decimal approximation here, then this is what you're going to do. You're going to punch natural log, and it'll open up parentheses for you, and then you go 15 over 7, see, because that's all one argument, and then you close the parentheses and press equal, and you'll see that that's approximately 0.76. Now this is not like the last one where we had ln of one thing over ln of something else. This is all one argument. So you do ln, open parentheses, should automatically appear, and you do 15 divided by 7, then close the parentheses and press equal, and you'll have 0.76. And here's another example for us. 2 to the x minus 3 equals 52. Now, although 2 is a factor of 52, 52 is a multiple of 2, 52 is not a power of 2. See, 2 to the 5th is 32, and 2 to the 6th is 64. So this, we skipped right over 52. This answer is going to be, this exponent is going to be somewhere in between 5 and 6, probably a little closer to 6. But then we have to subtract 3 from it, and it's not a whole number, so we're going to have to use the natural log to help us get there. Let's take the natural log of both sides, and after we do the natural log of both sides, we're going to use the power rule to take the exponent and put it down in the coefficient position. And then we'll have to get rid of this ln2, kind of acts like a coefficient, but we'll divide it away. So let's divide both sides by ln2, and we have x minus 3 equals this fraction. Now this is not a whole number, and you cannot simplify this into ln of 26, because remember our quotient rule says that if you've got a division, you could write it as a subtraction of 2 logs, but this is a division of 2 logs, so it's not the same thing. You cannot simplify that fraction there. It's just ln 52 over ln 2. And now we're going to add 3 to both sides. And you could use your calculator to figure out a decimal approximation. And in this case, if I punch ln 52, close the parentheses, divided by ln 2, close the parentheses, and then plus 3, we're going to get 8.70. So remember I said that this exponent would be somewhere in between 5 and 6. Well, if you do 8.70 minus 3, it's 5.7. So that is indeed somewhere between 5 and 6. Alright, here's another one. Let's solve 3 to the x over 2 equals 5. Now 3 and 5 cannot be written as the same base. So we will simply take the natural log of both sides and then use our power rule to move that exponent down to the coefficient spot. Okay, now let's divide both sides by ln 3, because all we're trying to do now is isolate the x. So if we divide both sides by ln 3, there you have that. And now I want to get this 2 on to the other side. So let's multiply both sides by 2. And there you have that. Okay, so we could use our calculators to get this decimal approximation. You could punch 2 times natural log 5, close the parentheses, divided by natural log 3, Close the parentheses if you like, and press equal. And that comes out approximately 2.93 if you round off. Okay, another one. 7 to the x equals 4.6. Well, let's do the natural log of both sides. Use our power rule to move the x down to the front and divide both sides by ln 7. And then you can use your calculator. ln 4.6, close the parentheses, divided by ln 7 equals approximately 0.78. See, it's just the same pattern over and over. So once you get used to the process, it never changes. You just want to make sure before you start that the base and the exponent are by themselves before you do this natural log to both sides step. So just to recap what we're doing. Isolate the exponential term. Take the natural log of both sides. Use the power rule to get the variable out of the exponent. Then you're going to isolate x using whatever equation solving skills you have to use. And that's all that you really have to do. Use a calculator to get decimal equivalent if you need to. You don't always need to, but sometimes you might be asked for that. And there you have it.